Have you ever noticed how even when a wire is not connected to a battery, it still contains energy? That's because the electrons inside it never really stop moving. In the absence of an electric field, electrons in a conductor move randomly due to thermal energy. It's like people running in different directions in a crowded station. No one goes anywhere collectively. After every collision with fixed positive ions in the metal, an electron continues moving, but in a completely random direction. So, the overall effect: no net movement. Mathematically, we express this as V bar equals 1 divided by n multiplied by the sum of V sub I, where I goes from 1 to n. This comes out to 0. As you can see in the diagram, there's no preferred direction of motion, just pure randomness. Now let's apply an electric field and watch what changes. Suddenly, every electron experiences a force opposite to the direction of the electric field. This force is given by the equation F equals minus E times E, where E is the charge of an electron and E is the electric field. From Newton's second law, this gives us A equals minus E times E divided by m, where m is the mass of an electron. Electrons now accelerate uniformly in a specific direction, though they still collide and bounce. But with every interval between collisions, they gain a bit of speed in the direction opposite to the field. Now here's the key idea: even though each electron's motion is erratic, there is a tiny average shift in its direction. We call this drift velocity, and it's responsible for the flow of current. Let tau be the average time between two collisions. This is called the relaxation time. Then, we define drift velocity as V sub A equals minus E times tau divided by m. This means that each electron drifts slightly in the direction opposite to the electric field. And this slow, steady drift, though small, is what produces electric current. In the diagram from your textbook, we see how the electrons, after multiple collisions, show a slight shift forward, the drift. Let's now connect drift to something measurable: electric current. Let it be the number of free electrons per unit volume, and be the area of the wire's cross-section. Now, in a tiny time delta t, electrons drift a distance of V sub A times delta t. So the number of electrons passing through the area A is n times A times V sub A times delta t. Each electron carries a charge E, so the total charge transferred is n times E times A times V sub A times delta t, and therefore current I equals that total charge divided by delta t, which gives I equals n times E times A times V sub A. So the bigger the drift velocity, or the more electrons available, the higher the current. Now comes the magic. Let's derive Ohm's law from this microscopic viewpoint. Current density, which is current per unit area, is given by J equals I divided by A, which equals n times E times V sub A. Now substitute the formula for drift velocity. V sub A equals minus E times tau divided by m. We get J equals n times E squared times tau times E divided by m. From this, we identify conductivity sigma as sigma equals n times E squared times tau divided by m, and so we finally arrive at J equals sigma times E. That's Ohm's law, not just a rule, but a consequence of microscopic electron behavior. Let's try out these formulas with a real example. A copper wire of area 1.0 into 10 to the power minus 7 meters squared carries a current of 1.5 amperes. Given E equals 1.6 into 10 to the power minus 19 coulombs, N equals 8.5 into 10 to the power 28 per cubic meter, we use the formula V sub A equals I divided by N times E times A. Substitute the values. V sub A equals 1.5 divided by open bracket 8.5 into 10 to the power 28 times 1.6 into 10 to the power minus 19 times 1.0 into 10 to the power minus 7 close bracket. This gives V sub a is approximately 1.1 millimeters per second. Yes, that's all. Even a strong current corresponds to a very slow drift velocity. Now let's define something called mobility. Mobility, denoted by the Greek letter mu, is the drift velocity per unit electric field. So we write mu equals VA divided by E. From earlier, we saw VA equals minus E times tau divided by m, which gives us mu equals E times tau divided by m. This tells us how quickly an electron responds to the applied electric field. Materials with high mobility conduct current more easily. You'll see in the animation how materials with higher mobility show longer drift arrows, indicating faster flow. Let's quickly go over what we've learned. Without an electric field, electrons move randomly and no current flows. When an electric field is applied, electrons drift, and this produces current. The drift velocity is given by V sub a equals minus E times tau divided by m. The resulting current is I equals N times E times A times V sub a. From this, we get the microscopic form of Ohm's law, J equals sigma times E, where sigma equals N times E squared times tau divided by m. So we've gone from thermal jiggling of electrons to a macroscopic law that governs circuits in your house and your phone. I hope this helped you connect the dots between physics theory and everyday electricity. See you in the next lesson, where we explore the limitations of Ohm's law and understand when and why materials disobey it.